Science Department at Chennai Mathematical Institute. She also held an invited professor position at ENS Paris-Saclay and visiting faculty position at IIT Bombay and a member of Relax. In 2009, she got the Google Women in Engineering Award. Before joining CMI, she was a researcher at Uppsala University, Sweden. And before that, she got her PhD from ENS Cachan, which became Paris-Saclay. So over to you, Aiswarya.
Thank you. So, can you hear me? Yeah. Thanks. Let me check that the boundary is working. Okay. So, what I want to say here is that this is so this is not a tutorial. It's not a survey. It's only going to be a very general introduction. So I hope you all will be able to follow. So, and if you do not follow, you should ask me questions. Okay, this is the first thing. Second thing is it's based on a chapter that is yet to come in this book on games on graphs by this Fialkov et al. There's a joint chapter with Paul Gaston, who is from LMF ENS Paris-Saclay, and Natalie Schneider from Lip6 Paris-Sorbonne. Okay, so we will start with the game. So here there are, by the way, remember the title is Synchronous Distributed Games. There is some distribution and there's some synchronous. Okay, so this is a game in which there are two players, this blue person here and this red one. So Alice and Bob, let's say. And there are like three objects here, which are three dices, but it's not really for probability or random throwing or something. So this yellow star is the dice that is going to be placed by the environment. I said placed, not thrown. Okay, so you place the dice to put some value. So this guy here, so these black things are like tall walls, so you cannot see each other. So this guy here, she can see both this black dice and this blue dice, and she can change the value of the blue dice as she wants. Okay, and this red guy here, he can see the blue dice and this red dice, and he can change the value of the red dice as he wants. And the objective is to make sure that the sum of the values of this dice is odd. Okay, so can you do this? So how does it proceed? So initially, it's like this rock, paper, scissors. So you keep your dice with you. 1, 2, 3, go. You place the dice. Okay, like this. And then you have to say, you have to see whether the sum of the dice is odd in every round. Okay, then again you do this. Okay, 1, 2, 3, go. Then the next round. Is it, so of course you have the information of the full history, you can store whatever you want, but you have to do it like this. The blue and the red players are a team. Together they have to come up with a strategy which makes sure that the sum of the dice is odd. Can we do this? How do we do this? Yes, Risha.
The environment plays odd, then you both collaborate, then you be like both of us place even.
But you don't, yeah. So that's a good strategy. But the problem is that you do not see that thing and you do not get the time to respond. It's like rock, paper, scissors. So yeah. So you need to know what is the I mean what you have to kind of guess what they're going to do and do this thing. And hence, in fact, there are cases when you will not win. So this thing will not have a, so just to recall that we are playing in rounds, and in each round the environment plays this black dice and the two players place their respective dice, and the objective is to get the sum. And this one will not have a winning strategy. Okay, the thing is that you need to have a delay. You need to be able to observe what the environment did and then respond to it. So instead, if I change the objective now, what I want is again the sum to be odd, but I want the sum of the red dice plus the sum of the blue dice in the previous round and plus the sum of the black dice in 2 rounds before that. If this is what I want to make sure that it is odd, this indeed you can do that, right? How will you do it? I mean, yeah, there are several different ways, but then you can think of some way of doing it. Let's just say that, there are like two environment places here now. Like one is this black dice and one is this gray dice. So environment will throw these two, and the objective is now is to make sure that the black plus gray plus red 2 rounds later is odd. Why I want this 2 rounds later? Because somehow the value or some information about this thing needs to be propagated to the red player, and that needs this delay. Okay, so blue dice is not really in this objective now, but still the player is relevant. The player needs to transform some important information through her dice so that the red can finally place the red dice accordingly so that the objective is accomplished. So in short, this what I just showed here, this is the architecture. So architecture describes what are the players, the locations that they control, like what they can read and what they can write. So this thing is given by the architecture. So for example, this particular architecture we saw and we are seeing now is represented by this is the architecture. This is how we pictorially represent that. So we have these two players, Alice and Bob. Alice is the blue one, red is the black one. Bob is the red one. There are these two players, and there are these three places or three locations, which are like the three dice. Okay, so Alice, the blue player, can read the value of the environment and can write onto A. Of course, it can also read from A, but that is a redundant thing, so we are not indicating that. And Bob can read the value of this dice A, and it can write on the value of the dice red. And of course, this since it's an environment, we don't put this as a special player or anything because we are not interested in what they will be doing. No matter what the environment does, the players have to collaborate to reach the objective. That's the idea. So this is the place where there is no writer, but basically the environment writes to that. Okay. And this particular architecture where you have this one more dice, this is the dice F now, the location F now, which is also read only by Bob. That is how you represent this architecture. The architecture kind of says which are the players, which are the locations, and what is the read-write relation between them. So to give a bit more examples, this is yet another architecture, okay, which we will also see later in the talk. So there are just two players, P and Q, and there are 4 locations. So U and V are the environment locations, and U prime and V prime are the locations on which the players are going to put values in, and there will be some objectives. Maybe the objective is to make sure that U prime and V prime are exactly the same across all the runs, which is maybe they have, if that is the requirement, can they win? That U prime and V prime should be exactly the same in all the rounds. Yes. Yeah, they don't need to look at the input at all. They can just agree that we just output zeros all the time, for example. So this thing is winnable. On the other hand, if you also ask that U prime should be equal to U, V prime should be equal to V, and then something extra which is connecting U and V, it's a bit more complicated because there is no communication between P and Q, and hence things can become. Yes. So I did not say the winning condition yet. I did not say what's the final state also. So in that objective that I said there, in every round, the sum has to be like this. So as you continue. So okay, so this is yet another architecture. So with many more players and with all kinds of reads. So there are also these red edges that I have shown here. These are like, this is similar to, so I said that when the player P1 is writing to U2, indeed he knows or she knows what's the value in U2. So you can put a back edge, but that is not really important. And similarly here, these red edges are also like a back edge, which is not really, I mean, it's really redundant edges. The reason is that, so if you look at here, it's both P1 and P2, they are reading from, so there are only 2 environment places here, U0 and U1. And both of them are reading all of those inputs. So since beforehand they can agree on what is the strategy of all the players, so P2 already knows what P1 is going to write on every combination of this U0, U1 that is going to see. So it already knows the values of U2. So this red edge is not going to be very helpful. Even if it is not there, it's the same. Okay, same way P2 will, same way P1 will also know what U3 is going to be because it knows the strategy of P2, because the players can agree beforehand what strategies they are going to play. And because of that, it will also know what is the strategy of P3, right? Because it knows the strategy of P3, it knows what U3 is going to be, it knows what U1 is going to be, so it knows what values it is going to write on U4 and U5. And similarly, since the strategy of P4 is also public, it knows what is U3, it knows what is U4, hence it can deduct what it is going to write in U6 and U7. So this edge is also, this red edge is also redundant and so on. So, but the architecture does not forbid it. You can also put these edges, but there may be some redundancy. Yes.
Sometimes the P1 also redundant, because anything that P1 can read and write is also seen by P2 also.
Yes. Yes, so there are two players. So we are right now there are two players. What I'm saying is that why do we need these two players? Instead, only one player is enough. But the thing is that only P1 has write access to U2. P2 cannot write what P1 wanted to write there.
But nobody reads. So P2 will just keep it.
No, but maybe the objective would require that the value of U2 should be something, and then in that case you need the U2. Yeah, of course, if the objective did not have anything about U2, you can just, yeah, you don't need to worry about that. Okay. So the features of this synchronous distributed games is that there is partial observation, which is given by this architecture, and the location, you can think of this location somehow as a local finite graph. Okay, but here, because we are placing the values, we just think of the graph as a click. So so in this example, there were like 6 values. You could put any of the values. The player can put any of the values. The global arena, when you think of game, there is an arena, and this architecture is definitely not the arena. The real game arena is actually the product of the locations, the product graph of these things. So essentially, a global arena would say that, okay, the black has value 3, the blue has value 2, and the red has value 1. This is one global arena. From there, so there's a strategy profile. Each of the player will make a move, and then the global node or global arena vertex will get updated by its move. Okay, so there's a partial observation, and what you can observe is kind of determined by the arena, by the architecture, and the arena is the product of these locations. And we do not allow multiple people to write onto one location, because then we do not know who writes first and what is overwritten, etc. So we make sure that every place can be written at most by one player. Okay, so these were the architectures that I showed you. And now the winning condition. The winning condition is going to be a regular condition on sequence of global nodes that is visited. So we can ask for infinitely many or parity or whatever condition on this global nodes visited. So for those of you who do not know this infinite words, some students, don't worry, you can also assume it to be some finite place and then some finite state automaton, which kind of describe the global sequences of nodes, which is triples of.
There are formal definitions coming.
No. And yes. Yes, in this product graph, the sequence of nodes visited. Okay, so in fact, we can even use local atomic propositions. That is not a problem. I'll give an example here. For example, you want to say that the blue and red die should not have the same value in 2 consecutive rounds, in any 2 consecutive rounds. So you can say things like that. Or you can also express this thing in suitable temporal logics also if you want, but that's fine. Or maybe the maximum value seen in blue is more than the maximum value that you see in red. You can also put some infinitary condition, like you can say that the maximum value seen infinitely often, etc. So any kind of omega regular condition that would involve all of these product locations. Okay, this is the winning condition. So this is the game setting. So you have an architecture, and in each of the locations in the architecture there are some finite set of values that it can take, and an objective which is given by an omega regular condition on the global state sequences that you are going to visit. Yes, and the players play as a team. Is the game clear to everyone? Okay. And what are the questions that we ask? Of course, given a game like that, we want to know whether the team of players have a distributed winning strategy and what is a distributed winning strategy. So each player will have a local strategy, which is it can only observe the values that it can read, or it can guess about the future, not guess, it can determine about the future as knowing the other things. So just reading the values of the read values. So from any sequence of read values that it has seen so far, from that history, it has to determine what is the value that it was going to write on any of the right locations. Okay, and a distributed, so you have a local strategy for each player, and a distributed strategy will give a strategy profile. So each player will have to play according to their strategy. So it's a tuple of strategy, one for each player. So that is a distributed strategy. So is there a winning distributed strategy? That's the question that we want to ask. Yes. They are determined. Yeah. So, and if they have a winning strategy, do they have a finite memory winning strategy, distributed winning strategy all the time? So these are the questions that we are asking. Okay. Now, any guess for this theorem? Undecidable. So does the team of players have a distributed winning strategy? This is an undecidable problem. In fact, it is neither RE nor co-RE. So this is the only result that I will present in the, like I will try to give the proof for in this thing. And already this is the case for this very simple architecture with only 2 players. This is the architecture that we saw before. There is no communication between P and Q, but the play proceeds in rounds and all that. So as we said before. And the question is, given some omega regular winning condition here, is it, does these 2 players have a distributed winning strategy? And this is neither RE nor co-RE. We give a reduction from this particular problem, which is given a Turing machine, is there a word that does not halt? The existential non-halting problem, okay, which is neither RE nor co-RE, Rice's theorem. Now, what is the reduction? So the architecture is already going to be this one, right? We need to decide what are the values that we are going to give to these locations. And we need to decide what is the winning condition that we want to come up with, such that there exists a winning strategy, distributed winning strategy, if and only if there is a word that does not terminate. That's what we want to do. So this reduction is the only technical result that I will show, which I also think that all of you will be able to follow. So if you do not understand, please stop me and ask me. So how much time do I have? Okay. So this is the problem that we are after. Now we want to try to reduce from. So somehow these are the values that I want to be in the location. So this is a sequence of values that's going to appear in the U location. This is the one in the V. This is the one in U prime. This is the one in V prime. So U and V are Boolean locations. The values are going to be just 0 and 1. U prime, V prime. Basically, I want to encode the tape configuration. So all the tape alphabet can be possible values in that location, plus an extra padding hash. And this is the tape blank symbol, this empty set. Okay, and since I want to represent the configurations, I also want to put the states of the Turing machine inside. But this is okay. I mean, I am using it like this, but if you want to do it to the binary, that's not a problem. You can still convert it all into a binary with a fixed length coding or something like that. So this is not the reduction. I'm just showing how the values are going to be. So the omega regular condition that we were talking about, it's going to be given by some finite state automata or a Boolean combination of finite state automata. Each of them which is going to read a letter which is like this, which is a 4 tuple of letters. So it's going to read the current in each round, the value of U, V, U prime and V prime. So it's going to read these 4 values round after round, and the condition is going to be like that. So what are the conditions that we want to say? We want to say that if u and v receives the same input, then the outputs must also be the same. U prime and v prime words must also be the same, exactly be the same. And this is something that you can say in, like, I mean, actually, I do not care about the full input. I look at, so the inputs are also always going to be, it's also from 0 star, 1 star, 0, and then something. The remaining inputs I do not care about. Okay, so there will be some zeros and ones and all that. So the first one block, it's going to be ended by a 0. So this is important. And if this 0, which kind of marks the end of the one block, they appear at the same level, then I want the u prime and v prime to be the same. So it has same number of ones. Okay, and there are some padding zeros before, and it ends here. Then I want the outputs to be exactly the same. This is my first condition. The second condition would say that if there is a single one, then the output should be the initial configuration of the Turing machine on some word. So you will put some padding. So one more sharp for this 1 and one more sharp for this 0. After that, you will start outputting the real Turing machine configuration. It should start from the initial state of the Turing machine, followed by some initial word, some word that is going to read on the Turing machine tape, followed by the blank symbol. Of course, if it's omega regular, then it will be omega, but it's fine. Even finite words are also fine. Okay, so if it is the length of this one block is just 1, then it has to be the initial configuration. Then if u gets a k length one block and v gets a k plus 1 length one block, then we want v prime to be the successor of u prime. Here I have put, I have adjusted the length in the padding before, so that the zeros are again aligned, and that is what I have displayed here in the picture. So if you can see that the length of v, the one blocks in v, is actually 1 plus the length of the one blocks in u, and the end marker or whatever, this 0 is aligned. So then I want it to be producing these sharps until here. Then after that, here you have some Turing machine configuration. I mean, that's what I would expect. Then this particular output should be the successor of this one, which I can now write in finite state automata with those tuples as letters, right? I mean, you can also write it in LTL or something like that. You do not even need the full MSO for this one. You just need FO. K is some number. So somehow intuitively K is supposed to, if it was K, we will see later that we will enforce that the corresponding output should be the kth configuration of the Turing machine. So this is like the first configuration on the word W. That would be the kth configuration on the word W. That is somehow what that we will enforce later. At present, I have not said that, but just saying that, and if it is a Turing machine configuration, then this one should be the successor of that. So here the transition is something like you read the A and then you move to the left, you replace this A with a B. So you have replaced that A with a B and you have moved your head to the left, you went to the state Q prime. And anyway, you know that this is only going to affect these few cells here, a window of 3, which you can kind of memorize in your state and you can check that it's happening. So this is this condition that, so here it's important that the zeros are aligned, okay? So otherwise we cannot do that. Of course, if something is ending here and this one is ending way after with a lot of padding, these successors are going to be, these configurations are not going to be in sync, and then we cannot check that they are equal. So this we can say. Now, we can increase the padding and the value should not change. That is what this condition is saying. It's like, so U and V are almost the same, except that V is shifted by one more padding letter. In that case, the corresponding output should also be shifted by one more padding letter. That is the next condition that you would say. Okay. And then we will say that the output should never contain the halting state. We want it to be non-terminating, it should go on. So this is it. These are just the remaining condition is just a conjunction of these 5 conditions. And this is my reduction. Okay, so given a Turing machine, we will construct. So the architecture is just this one. And the values, as I said, U and V are going to be taking binary values. U prime and V prime are going to be taking values from the type alphabet union states union hash. Okay, and these are the 5 conditions that I'm going to write. And these are all just regular conditions. You can come up with finite state automata for each of these things. Yeah. Now, what does this imply? So I claim that this is a reduction from this problem. So if with this winning condition, if there is a winning strategy, then that means there is a word that does not terminate. Okay, first of all, let's see that if there is a word that does not terminate, then there is a winning strategy. So their strategy would be that, okay, they agree beforehand, let us pick this word. This is going to be our candidate word, which is not going to terminate. And we will just simulate this Turing machine on this word. And if my input is asking for some 0 power L, 1 power K, then we will output the kth configuration on that word. This is our strategy. So they can agree on this strategy, and then all the conditions would be satisfied. Okay, so on the first configuration, this is what it is going to output. And of course, if they are the same, getting the same thing, they will be the same. And anyway, you will start outputting only after this delimiter 0. So that is also fine. So if there is a word that does not terminate, then they will have a winning strategy. The other direction is the more tricky one, which is to show that if there is a winning strategy, then there is a word that does not terminate. So we do not, the thing is that these 2 players do not know what is being given as the input to the other player and how they are going to, they must publicly announce their strategy beforehand, but they do not know what is the input that is going to be given. So in order to succeed, say if they were given like 0 power K1 and 0 power K1 to both U and V, they both should output the same thing. Okay, and that should be an initial configuration. So it should be an initial configuration according to 2, and according to 1, they must be the same. So they have to agree on the value that they have to give if it was 0 power K1 as the input. Okay, that they have to agree. And so they have to fix some word for that, both of them. So let's keep it to be the V, keep it to be this W. Then we also know that if one of them is just extended by 1 more 0 before, then the other one should be extended by 1 more sharp. So if the input was just 1 0, then you should have outputted the initial configuration 1 0 on both. So now if I get 0 1 0, then also I should output the same thing with some sharps in before, because maybe the other guy is now getting just 1 0. And in 1 0, we know that guy is going to output Q0W. So now I should output hash Q0W, something like this. Okay, this now I know that if they are getting 1 0 before, they are going to output the same. Now I know that if I get 2 zeros, maybe the other guy is going to get 1 0. I know how he is going to behave. So for 2 zeros also, I should output the same thing with 1 more sharp. So we do not know what the other guy is going to get, but what if he was getting that, then I need to output this, etc. Because of this thing, we kind of know that no matter how many zeros you put before, when you see a 1, it has to be the same word that you have to output. Okay, so the length of this padding can be arbitrarily big, but if it is with a 1, then I have to output the same word. It's already an induction going on. So because this fear of what we do not know what is the input to the other one and what that guy is going to be given. So we have to agree with this initial word, and we have to continue with this same initial configuration, no matter how many padding zeros are there in the beginning. Okay. And then the next thing is, now we know that if one guy is given just this one and the other guy is given with the same padding, K plus 1, like that guy is getting 0 power K1 and I am getting 0 power K2, 2 ones. Now I have to give the second configuration because it is required here that this V prime is a successor of V prime. And so I know that if I am getting, so I know that guy, if he's getting 2 ones, he will be outputting the second configuration. So if I'm getting two ones, I should also be outputting the second configuration, because I say that if they are the same, then the outputs must be the same. And if that guy is getting 2 ones, he's going to output the second configuration. So if I'm getting 3 ones, I should output the third configuration on that particular word, because of the successor relation. So on and so forth. So hence I can argue that the only winning strategy here, or the only strategy that is feasible, is that you agree on some word, and if the input is of the form 0 star 1 power k 0 something, the output must be padding hashes, then the kth configuration of the Turing machine on that word that they agreed on. And it should never enter a halting state, which would mean that for whatever k it is given as the input, you should be able to output a configuration there. So hence, this is a non-terminating run of the Turing machine. So if they have a winning strategy, then from the winning strategy, we can extract a word, and on which this particular Turing machine is not going to terminate at all. So the full word is not given, it's just finite run, and it's just out of fear of we do not know what is going to happen the other side. You have to just play nicely and correctly. Okay, that is how this reduction is working. So this very simple architecture that you see up here with only 2 processes, this is undesirable. I mean, not just undesirable, it's neither RE nor co-RE. So yeah, so the fact that it was not co-RE was known before. Yeah, we have this full proof which also says that it's not RE even. How much time do I have? Okay. Now, what about this architecture? There is some connection between them. So after this U prime, so whatever this guy produces as the output, this Q can read, and whatever Q produces as the output, P can read. Is it going to be desirable here? What do you think? So even in this architecture, it is not going to be desirable. It's more or less the same proof like this one. The thing is that even if you have this extra thing, you can the specification can force it to mask whatever it was outputting. For example, what it can do is the input, let's say that in every odd bit, what it's going to output is the actual input that you wanted. In even bit, the inputs U and V will be some arbitrary zeros and ones. We do not know what this value is going to be. And the specification would force you to do an XOR with the even number bit. Whatever you wanted to output there, you do an XOR with the even number bit and then output it. If you do that, so what you see is at every point is some zeros and ones, okay, sufficiently random. You have no idea what was the XOR bit that you used. So you have no way of guessing what the actual bit was going to be. Of course, here the outputs in the reduction that I showed you, the outputs was with the tape alphabet and all that, but you can convert it into binary with some length encoding. So it's not a problem. And then let's say that you are just doing it like this.
Actually, previous section I did not get where you get the command to store.
We are not storing the configuration.
Somehow you not that.
What am I doing? Sorry. I was trying to. Yes, that is actually in the winning condition. So yeah, so that's what. So you never give this thing into the players, never actually produce anything. But because of the fear of what the other guy is going to be given as the input, you are forced to output the correct answer all the time. Yes.
All determinants, then play termination.
No, that's not what it says. If there is a word on which it does not terminate, it's exactly the opposite of what you said, then the players have a winning strategy. Yes.
But it doesn't, that they don't have it.
Yes.
And all words that we have done is 5 1 words.
Hmm?
5 1. Unlimited.
Yes.
Nothing of money or any.
Yes.
Right. Yeah.
Yes. And this problem is also highly undesirable. Yes. Yes. Prakash, is it okay? Is the reduction okay? Is the reduction okay to everyone? Yes.
In this case, P will produce just one configuration if the input is of this form.
P will produce just one configuration. So yeah, so P does not know what is going to be given as input to it. So the thing is that suppose it has some other strategy, it produces on seeing the 0 power K, 1 power L, whatever, it is producing something, some arbitrary thing. The environment could have possibly given just the 0 power L K minus 1 on the other thing, and then that is now going to violate condition 3.
Okay.
That is what is going to happen. And there is no way of, so they say that, okay, now if you were given K and I was given K plus 1, let's produce it on the word W prime. They cannot cheat there. The thing is that you do not know what was given to that guy. So maybe that was given the configuration before. Okay, and so you can kind of inductively go down on this K, and you may come back actually to this 1 1 case. So you have to kind of, so if it was 1 here and 1 there, then we have to agree on the word. So that word has to be the same. Okay, so I know that if it was given a 1, that guy is going to play exactly this thing. So now if I'm given a 2, I know I will have to play this. That guy also will have to play that. So on 2, I know that he is going to play that. So hence, if I'm given a 3, I have to play the third configuration, because on 2, he's going to play the second configuration. On 2, he's going to play the second configuration. 2, I will to play the second configuration. So on 3, I have to play the third configuration, because maybe he is going to be queried for 2. And if he is going to be queried for 2, he doesn't know what I am being queried on. So he may think that I am being queried on 1. So he will play the 2. So now if I am asked 3, I have to play the third thing. So this kind of reasoning of what if he was given that, what would he be thinking that I will be doing? And what would I be doing in that case? So this, assuming that he was doing that thing. So this kind of zigzag kind of reasoning goes on inductively all the way down to this 1 1 case where they had to agree, and hence it will be this one. Yes.
So here, saying anything more about this strategy in the sense that no memory restriction or anything like that.
Sorry, can you say again?
So not saying anything more about the strategy in terms of having a memory restriction.
No, at the moment we are not worried about memories at all, finite memories at all.
Right.
It's just about, does there exist a strategy? So you can use all the memories that you want. You can use a Turing machine tape. You can store everything, whatever.
So
Is there a
some
strategy?
strategy, some big
Yeah.
kind of computation
Yeah.
can happen for
Yeah.
that. Yeah. Okay. Sure.
So
But the power comes from the fact that.
Yeah, maybe for the two people to hear.
Strategy, right? Yeah.
The power comes from the strategy. Yeah, you have to make a deterministic choice. Yes.
Yeah.
Yeah. The strategy is deterministic. It's a function. Yeah, that is very important. And also the power comes from the fact that you have no communication. So you have no idea what the other guy is being queried on. Is this okay? So now coming back. So on this architecture, we saw that it's not decidable. And what about this architecture? So now I can get to know what this U prime or V prime is. So if it was following exactly the previous strategy, now I know that when the sharps have stopped and when I am starting to see a ones and zeros there. So I know that this guy now is queried for at most the third configuration or fifth configuration. Now if I am asked for some 19th configuration, I can cheat because I know that the other guy is asked for a much smaller configuration. It's not the immediate successor. So, but can this give more power? This is what I'm saying, that this also you cannot. For the moment, to make this work, let's assume that now U prime and V prime are on binary outputs, which we can convert, right? Some fixed length encoding in binary. And in this output, what we will do is, we will just, the environment will just make sure that the input is actually given on only the even bits or odd bits. So one of the, let's say odd bits, like 1, 3, 5, etc. are the actual inputs which we want. 2, 4, 6, etc. are going to be the mask that I want to give. It's like the encryption bits. So I give you this extra bits, and the specification would also ask you, instead of outputting just the value that you wanted to output, you output the OR with the mask bit that was given to you. Okay, so this is what you have to output. So you have to output something which is masked by this XOR, not the OR, XOR, by the XOR. So if you got an XOR output, so it can be either 0 or 1. If you do not know the mask bit, you have no way of recovering what the value was. So even if you are reading this U, it's almost as good as you did not read it. It's not going to convey you anything meaningful, because you are just going to see some garbage zeros or 1. You have no way of identifying what part of it actually made sense, when, what was the actual output or anything of that sort. So even if there is this kind of feedback, this is not really going to help. You really need to know what was the input given to P. This is what is finite.
For any finite feedback also the same trick probably will work.
Finite what?
Feedback, I mean, any K, if you have a,
Yeah, so here there are only 2 locations. I don't understand what is finite feedback.
no, I mean, if this guy can see what that guys did two rounds
Yeah,
back.
so they have infinite memory, so they can store everything. So whatever they have seen from beginning until now, they can store, including the entire history of values that appeared in V, including the entire history of values that appeared in U prime. All of this thing is available to Q, but still he cannot make any sense out of it. He can only, it's only as good as knowing what was given to V. If he wants to know what was given to U, you need to know U itself. Just because of this masking that is demanded, from U prime we cannot deduce back what U was.
Okay, you're saying, okay.
Yeah, so Q does not know what U is, and P does not know what V is. This is the problem. So even though there is this feedback, the specification can require you to mask the real information that you want to transfer. So this architecture also is hence undecidable with this extra masking technique on top of the previous reduction that we show. In fact, no, neither are in our PORE. And it is the case even if you started with this use, this was the only environment input, you will produce something. So P1 will know actually all the things, okay? Here, because P1 is going to produce this U1. P1 knows what is written in U1. P1 know the strategies of all the players are publicly known. So P1 will know what is the value which is going to be written everywhere. P2 would know, except for, so U1 is given to him. So it doesn't know what is the value of U0, but other than the U0, everything else P2 is aware of in this architecture. And then P2 can write to U2 and V2. Since P3 can see both U2 and V2, P3 can know also what is going to happen in this part of the world. Everything in U2, V2, U3, U prime, V prime, all of those things, but not U1 and U0. Okay. What about P? P can know what U3 was there, or what is in the U3 and what it is going to write in U prime. But it also sees what is written in V prime, but it does not know what is V2. It's the same kind of thing that was happening here, because probably the specification will ask you to mask the value of V2 when it is outputting on V prime. So P is not knowledgeable about V2, the values in V2. And similarly, Q is not knowledgeable about U3, because Q does not know what U2 is. If Q knew U2, then it would have applied the strategy for P3 and it would learn the value of U3. But since U2 is not known to Q, Q does not understand what U3 is, and P does not understand what V2 is. So between these two vertices, we can play again the same game. This feedback is not going to help. One direction or both direction, feedback is not going to help, because you can, in addition, ask the same masking technique in the specification. Yes.
Does it make sense to ask for the disability of a given configuration? So,
What of a
fixed architecture, you can value the objective.
Yes.
And maybe you can ask for
Yeah,
ethics
it
architecture.
is not studied, for example, for some particular, can you come up with a class of objectives for which it actually becomes decidable? So there is a lot more to study here. That's why I wanted to bring this topic up. So let me go over, I will come back to that question, okay? So this is, so as soon as your architecture has two players with incomparable information, it turns out that it's not decidable. In fact, and if the information is totally ordered, then it is decidable. So this is also there in our chapter, but I will not be presenting it in this talk. So some example where the information is totally ordered is the architecture like this. And as somebody was asking me, why do we need this P1 and P2? Because they almost have the same information. It is true. So we can actually merge them into a single one. And then we can go into some architecture like this. So they are equisolvable. If you have a strategy for this one, you can kind of distribute it and get this one and back. And here, if you look at it, there's a linear order between the processes, and the information is also like that. So P12 is the most informed because it knows both the environment inputs, and hence because the strategies are going to be public, it can learn the values of every other location. P3 on the other hand is strictly less informed. It will know U1, but it will not know U0. So it has information only about a strict subset of places. Okay, and so is P4, it has information about a stricter subset of places and so on. So this is what will happen. This is what I mean by saying that the information is kind of linearly ordered. The processes are linearly ordered according to the information, the values that it can learn about. That's what I mean. So if as soon as we have two processes in which, and there are two locations, two players and two locations that they cannot learn the values of, then it is going to be undecidable. Yeah. So in the case of this kind of totally ordered case, you can get decidability, but I will not go into that anyway. I was not planning to. The plan is to look at a monolithic thing, which everything is there, see whether that game is solvable. This you can decide, and then that is not enough. If there is no such strategy, you can say no. If there is a strategy, then you can again ask, can this strategy for this monolithic process, can it be distributed across the different processes? This is the next step. So that requires a lot of work, and that's going to be non-elementary complete, even in that case, the decidability. Just to tell you some quick bibliography, it's not all. So this model of synchronous games was introduced in this by Privelli and Rosner in 1990. Then the decidability, so which also showed that it was undecidable. The decidability was first shown for this for some kind of pipeline architectures by Kupferman and Wardy in 2001, and later in 2005, it was shown that so this message about this information fork or total linear order, the characterization of when it is decidable and not, was coming in 2005. These are some three just main, but there are many more works, for example, from CMI already, like, that time Madhusudan Parthasarathi and PS Tyagarajan, they have some work on this one around the same time in 2001 in ICALP. There is also Valukiewicz group who has worked on this thing. It's called distributed games. It was in FSTTCS 2004. So there are many things that I have not listed here, but some work like that. And now these days, I do not know of anybody who is working on this synchronous distributed games. But as the question that you asked, there are many more things that needs to be worked out here, and it is a challenging and not so much explored area with many questions lying there for you. Okay, so write it down, solve something, submit to FSTTCS next year. Deadline will be around June. Okay, yeah.
Thank you for that excellent talk. Are there any questions we can take about two?
Hi, so in every round, the environment input is kind of arbitrary, right?
Yeah.
So what if we know beforehand that it follows some distribution? Will it then kind of change
Yeah, so
the query?
we did not look at probabilistic or with some almost sure kind of winning strategy. We do not assume any kind of distribution. So we kind of assume the environment as a adversary who would know everything and who would also know the strategies and who would try to play so that the players do not win. This is the model that we are following. So no matter what environment does, the strategy profile of the players need to win.
No, but suppose we know beforehand that the environment plays with some distribution.
Yes.
Then does it change either RE or ORE? Stochastic gain.
Yeah, so then the question is about, can you almost surely win or can you do something like that? So I do not know about that. I have not thought about it, but that's again another direction to look at. I don't think these things are studied.
Thank you.
Yeah. So already this model of those with incomplete information. Extension of Gale's word. So
Information, imperfect information manifests here, but it is distributed.
So the question is already negative results when games with imperfect information. So when you strengthen, when you make that model complicated, at least we should expect some positive results unless so.
Positive results, I did not choose to
Okay, so what kind of positive results are there?
architectures like pipeline or the ones in which the information order is total. It is decidable. That is what I was trying to say in this slide. When it is totally ordered like this, then we have decidability. In fact, it is actually non-elementary complete for this one. But this is all with MSR specification. Can we go for weaker specification? Can we go for some more other kind of classes to get better complexity? This is always open. That's what I'm saying. There's a lot more to do here. Yeah.
Maybe one more question, if anyone has it.
Right.
Before we go and try to solve any problem that comes to mind, can you give a guideline on what may be interesting classes of problems to look at?
So I do not know to look to exactly answer that. So of course that is I think that's a very natural and nice direction if to look at the stochastic version. The question that you asked also, can you come up with for fix an architecture, can you come up with some class of specifications or objectives for which you can synthesize something? Of course, all these things comes from synthesis more or less. Like you view it as a game, but basically can you come up with a program to sit there which does this thing so that the final objective is kind of maintained. It's so for what kind of specifications can you synthesize a system? This is maybe not for the entire MSO synthesis, but maybe can you come up with some more restrictive questions? So that's actually, I think I find it very natural to explore. So already the undecidability holds for FO LTL. Okay, so we have to go below that, but what can we do?
Thank you so much, Aiswarya, for the excellent talk.
Thank you. Thank you. Thank you, the organizers, also for giving me the opportunity to give a talk here. Thank you.
We'll take a 20-minute coffee break and be back by 10:45. So we can start the next session. If you have more questions, you can.